welcome to Gifted and Science and Technology Physics class. I'm NC Joshua, popularly known as Oracle. Now we'll be looking at curved mirrors. Now let's consider a spherical hollow of this nature, and let's consider another hollow of this nature. Now if I shade the outer part of this hollow, it's not the same thing when the inner part of the hollow is shaded. When the outer part is shaded, it's showing us a concave mirror. But when the inner part is shaded, it's showing us a convex mirror. So the difference between a convex mirror and a concave mirror is to check where it's shaded. Which part is silver coated? Is it the outside or the inside? If it's the outside, it's concave. If it's the inside, it's convex. Now, the diameter of this sphere is drawn like this. This is the diameter of this sphere. So also is the diameter of this sphere. Remember that in a circle, so if this is the diameter of this hollow, the center of it is called the center of curvature, and the distance from here to this point is called the radius of curvature. I reiterate, if this is a diameter, half the diameter is called the center of curvature. So this is half also is called the center of curvature. Half is called the center of curvature, while the distance from the center of curvature to the pole of the mirror is referred to as the radius of curvature, that's r. But half the center of curvature is called the focus. So this is half called the focus. The distance from here to here, which is the pole, is arrow, radius of curvature, while half the center of curvature is called the focus. This line drawn as the diameter is referred to as the principal axis. So it means in a principal axis, I have the pole here. I have half of the line, half which is called the center of curvature, and half of this which is called the principal focus. So this line is called the principal axis. This is the principal axis, and on the principal axis, this point is now called the principal focus, because from here to the pole is called the focal length. So that brings us to a very smart question that can be asked. What's the question? In a spherical hollow, if the diameter of a spherical hollow is 20 centimeter, calculate the focal length. If the diameter of a spherical hollow is 20 centimeter, calculate the focal length. It means the diameter of a hollow is 20 centimeter. Half the diameter is the center of curvature, that's 10. Then half the center of curvature is the focal length. So the question says, I will write it here. If the diameter of a spherical hollow is 20 centimeter, find the focal length. So I can boldly say half half the diameter half the diameter equals your center of curvature. Then half the center of curvature equals the focal length. So how can this be solved? What is half the diameter? Half the diameter will be, so this, which is half the diameter, will be times 20 equals 10. So the center of curvature is 10. What is now focal length? Focal length equals half the center of curvature, which equals 1 over 2 times 10 equals 5 centimeter. So understand each of these points in a sphere. So we can now say that the relationship between C and F is that the distance between C and the pole, which is the radius of curvature. Note that, very important. The distance from the center of curvature to the pole of the mirror, of the curved mirror, is the radius of curvature. So, just as I showed you earlier on, the distance between C and the pole is the radius of curvature. Now, what's the relationship between the radius of curvature and the focal length? Therefore, it means that radius of curvature is equals to focal length. Therefore, focal length equals radius of curvature divided by 2. Take note of that. Now, the next thing I want you to know here is the various kind of mirror we can have. I have this to be shaded at the back, a concave mirror, and I have this shaded in front, the convex mirror. If a ray of light shines and strike here, it will converge, it will deviate it. If this is a ray of light, it will come over here, and this is a ray of light, it will come over here. Now, this point is called the focus. So the point where light ray converge is called the focus. But for this, a ray of light comes, strikes here. This is the direction of the light. A ray of light strikes here. It deviates. Another one comes. It deviates. This is the way it goes. Another one comes like this. It deviates. Another one comes again. It deviates. Now, what do we now have? We now have rays of light coming like this, coming like this, rays of light coming like this, and this coming like this. This is now called the focus. Remember, this is for a concave mirror. This is for a convex mirror. What does that mean? It means that a concave mirror converges light ray. Hence, it is called a converging mirror. While a convex mirror diverging light ray or a diverging mirror. So we have successfully said that a concave mirror is also called a converging mirror, while a convex mirror is also called a diverging mirror. Now, let this now take us to the kind of images formed in a plane mirror. Now we'll be looking at formation of images in plane mirror, in curved mirrors, precisely the concave mirror. Now let this be a sketch of the concave mirror, and we have this to be the pole, the center of the mirror. We have this to be the principal focus, and we have this point to be the center of curvature. We are looking first at objects placed between the principal focus and the pole of the mirror. Object placed between the principal focus and the pole of the mirror. This is how it will look like. It strikes the mirror and passes through F. It strikes the mirror and passes through F. Then another rays of light goes through this point and returns back through this point. Then we have a reflection of this here. Wherever it meets, that's where the image is formed. So we have this as image. Now I'll be using the thick line to indicate the object, and I'll be using a dotted line to indicate the image form. So this is the image. Now remember, object, object between F and P. The nature of the image form is the image is erect, the image is erect, the image is erect, the image is virtual, the image is magnified, the image is magnified. These are the nature of the image form. The image is erect, is virtual, is magnified, so we can have an acronym for that, which is VEN. The image is virtual, is erect, and is magnified. Now, I want you to know that a virtual image is erect and a virtual image is behind the mirror. This image is behind the mirror. A virtual image is erect. A virtual image is behind the mirror. Let's see another example of such again. This time, this again is the pole. This is our principal focus. This is our center of curvature. Now this time, I'm putting the object at the principal focus. It will be this goes and comes through F. Then this goes and returns. In this manner, the rays never meet. If they will ever meet, it will be at infinity, meaning the image form will be at infinity. Anytime the object is placed at F, what's the nature of the image form? The image is inverted. Wherever this image will meet, it will be an inverted image. The image is inverted. The image is and the image is magnified. Wherever it will ever meet, it will to be larger than the object. So if you have that in acronym, we have it as ring. Re, inverted, and magnify. I have a third diagram here, which will be this, which will be this, as we have it. This is the pole, this is the principal focus, this is the center of curvature. Now this time the object is placed between, this one is object, object number 2 is object at F, object at F, image, image, image at infinity. Take note of this, but this place image is behind the mirror. Now object between C and F. Number 3, object between C and F, meaning object between the center of curvature and the principal focus. What will happen is this: the ray of light travels in this direction and goes through the principal axis, then it will come down through the principal axis and go parallel, and go parallel, sorry about that, and go parallel, and go parallel to the principal axis. So it will meet somewhere here. This is the head, this is the head, this is the head, also this is the head. It means this is also the head coming this way. So it will meet here. This is the image formed. I told you the image will be in dotted lines. Now this is the object, but this is the image. The object and the image form is one, is inverted, is inverted. For it to be inverted, it is real and it is bigger than the object, so it is magnified. It is magnified, and the image is formed, image, image formed beyond C. Image is formed beyond C. What about if I have number 4, object, object at C? So this time I have it like this. Now this is the pole, this is F, and this is C. Now I have object at C. If I have object at C, it will be straight, goes through the principal focus, then hits through the principal focus and come back and meet here. So if it's meeting here, it means the image will be also at C. Object at C, image at C. Object at C, image at C. The image form is inverted. The image form is inverted. It is real. If it's inverted, it is real. Then another thing about the image form is that same size with the object, same size with the object, and the image formed, the image formed is at C. Now take note, there is something about image at C. The image formed at C is the same size with the object. So if the image and the object has the same size, we'll say magnification is equal to 1 because the image is not bigger than the object. What about I have this one? Let me put the last one. Let me put this one here. I have this one as my number 5. My number 5. The number 5 is object, object beyond C. Now, if this is the pole, this is F, this is C, object will be somewhere beyond C. Object will be somewhere beyond C. Remember, we've done object between C and F. That's what we have here. Now we are doing object beyond C. So I'm pushing the object. We started with object between F and P. The next one was object at F. The next one was object between C and F. Now we did again object at C. Now I'm doing object beyond C. Now if the object is beyond C, how will it go? The light ray will go straight and strike the mirror. Then it comes through the principal focus. It comes through the principal focus. Then the ray of light also passes through the principal focus and comes and hits here. Now check, this is the head. This is the head coming down to this place. So the image is inverted. The image is inverted. So this is the object, but this is the image form. Now, what is the nature of image form? In this case, the image is real, the image is inverted. If it's real, it's inverted. The image is inverted. The image is smaller than the object, hence the image is diminished. The image is diminished, and the image is formed. Image is formed between C and F. Image is formed between C and F. Mind you, look at number 3. Object between C and F. Image is formed beyond C, but object beyond C. Image is formed between C and F. You see the interchange? There are two cases that interchanges. The first case is object at F, image at infinity. There's another case, object at infinity, image will be at F. I reiterate, object at F, image at infinity, object at infinity, image will be at F. Image will be at F. Then we have another one, object between F and C. That's object between the principal focus and the center of curvature. Image beyond the center of curvature, beyond C. But we now have object beyond C. Object at beyond C. After center of curvature, you have an object there. Image is formed between C and F. Now, all of these cases helps us to know the right calculation using a ray diagram for formation of image, because if I know this very well, when I calculate a question, I can tell if the question is correct or not, because it will obey this principle. Now, for instance, if you check this whole diagram, there is only one case where a virtual image was produced. The only one point where the virtual image was produced is in this first case, where the object is between the principal focus and the pole of the mirror. The object is between the principal focus and the pole. The image was formed behind the mirror, and the image was erect and is virtual and it's magnified. So a question like a shaving stick, a man position his face between the principal focus and the pole of the mirror. What kind of image will the man observe? The man will observe an erect image, a virtual image, and a magnified image. So this is the only time a virtual image is formed by a concave mirror. Every other case, even the case at infinity, the mirror, the image is real and inverted. The case between C and F, it is real and inverted. The case at C, it is real and inverted. And even the case beyond C, the image is also real and inverted. Then the next question is check in which of these cases is the object, is the image magnified. In the first case, the image is magnified. In this case, the image is magnified. In this case, the image is magnified. In this case, the image is not magnified. It's the same as the object. Magnification is equal to 1. But in this case, the image is diminished. So all of these are things we have to know to describe an image. Thank you. Okay, let's see the formation of images now in a convex mirror. Now for a convex mirror, you have something like this and like this. Now if I shade the outer part, it's a concave mirror. But if I shade the inner part, it becomes a convex mirror. So imagine an object placed at this point. The rays of light strikes the mirror and it is diverged because it's a diverging mirror. Then these rays of light, now this is our principal focus. This is our center of curvature. Now the rays of light comes through here, so go through here. Then light from this point comes straight and they meet at this point. Where they meet is where the image is formed. So this is the image formed. Now if you check very well, the nature of the image form is vector, it is erect. Remember we said virtual images are erect. Then it is diminished. Now that means that this kind of an image is VERD. The short acronym for it is VERD. So what does that mean? It means that this kind of a mirror produces a virtual image, erect image, and a diminished image. Now this is the object. This case is seen in our driver's side mirror where the driver can see lots of cars behind him as though it is in front of the mirror. And so you have all of these cars in their diminished form for the driver to be able to see, have a wide view of how much vehicles are closer to him. So the driver's side mirror is an example of a convex mirror. Now, when you look at the position of the image, irrespective of wherever the object is, the image formed by a convex mirror is always between the principal focus and the pole of the mirror. Now, if you take this section and that of a concave mirror and sit with any past question, you see that you can eventually answer all of the questions. What might be the question? The question will be if a concave mirror is placed between the principal focus and the pole, where will the image be? And what will be the description of the image? All of those things I gave to you, just sit and take your book and take a question and go through it. You see that all of them are answerable. Now we'll be looking at mirror formulas, and this will be helping us to calculate questions as regarding mirror formulas. Now we'll be using the re is positive method, which is most appropriate to use for lesser confusion. Now, what is this formula? We have 1 over f is equals 1 over u plus 1 over v. What is our f? Our f is our focal length, our u is our object distance, and our v is our image distance. I want you to take note of all of these things I want to say, because once you can know all of these things I want to say, it will be much more easier to calculate this with this formula. First, for a concave mirror, focal length, which is f, is positive. focal length, which is f, is positive for a concave mirror, but for a convex mirror, focal length, very important you know this, which is f, focal length, which is f, is negative. What does this mean? It means if I'm solving with a concave mirror, a convex mirror, if it was told me that the focal length is 10 centimeters for instance, I will add a negative sign to it because the focal length for a convex mirror is negative. I will say something very fast here. The focal length of a plane mirror is infinity. Focal length of a plane mirror is infinity. Focal length of a concave mirror is positive, while that for a convex mirror is negative. Another thing I want you to note that will help you in solving this is that for a virtual image distance, what's our image distance, which is v, is negative. For a virtual image distance, which is v, is negative, but real images, image distance is positive. For real images, image distance is positive. Now, it might be something that you want to be confused. The word virtual might not be mentioned in the question. The word virtual might not be mentioned in the question. What should be the other words you should look at for? Look at for the word an upright image. Look out for the word an erect image. Look out for the word an image formed behind the mirror. All of these are of the same case, whether it is a concave mirror or a convex mirror. I reiterate again, if you do not see the word virtual, you look out for the word erect, look out for the word upright, and look out for the word behind the mirror. All of these are words used to connect a virtual image. So we'll be looking at some questions and you'll be seeing all of these things playing out as we do them. Now, please take note. You know that we said that focal length is equal to radius of curvature divided by 2. So anything applicable to focal length is applicable to radius of curvature. So if the focal length, if for a concave mirror, focal length is positive, radius of curvature also is positive. For a convex mirror where focal length is negative, the radius of curvature is also negative. So whatsoever plays out for our focal length is applicable to our radius of curvature. So next, we'll be looking at questions where we'll be applying these rules in calculations.